Welcome to this lecture on NMR spectroscopy, where we explore the key measurements that reveal molecular structures and interactions. These tools are essential for analyzing and identifying compounds with incredible precision, unlocking the secrets of the atomic world. Nuclear magnetic resonance spectroscopy, or NMR, is a powerful technique for studying molecules at the atomic level. It works by observing how atomic nuclei respond to a magnetic field, revealing details about how atoms are arranged and the chemical environment around them. The true strength of NMR lies in its key measurements, which provide precise information to help scientists identify and analyze compounds. First up, we have the chemical shift, denoted by delta, measured in parts per million, ppm. This tells us how shielded or de-shielded a nucleus is in its chemical environment. It's like a fingerprint for molecular identity. Next, integration. This measurement gives us the relative number of protons represented by each signal. Think of it as counting atoms without actually counting them. Multiplicity reveals how a nucleus is interacting with its neighbors. From singlets to doublets, triplets, and beyond, it's a symphony of spin-spin coupling. The coupling constant, or J, measures the interaction strength between nuclei. It's expressed in hertz, and provides precise information about molecular connectivity. Lastly, line width. This tells us about the relaxation processes and can even hint at molecular motion or interactions. Let's dive into the concept of chemical shift, symbolized by the Greek letter delta. This is one of the most critical measurements in NMR spectroscopy. The chemical shift refers to the position of an NMR signal relative to a standard compound, usually tetramethylsilane, or TMS. TMS is used as a reference because its protons are in a highly shielded environment, making its signal appear at 0 parts per million. The chemical shift is measured in parts per million, ppm. Why ppm? It ensures that the results remain consistent regardless of the operating frequency of different NMR instruments. This standardization makes it easier to compare spectra from various sources. The chemical shift is influenced by the chemical environment surrounding a nucleus. Electrons in the molecule create a shielding effect, reducing the impact of the external magnetic field on the nucleus. If the nucleus is more exposed, due to electronegative atoms or pi bonds, it becomes de-shielded, shifting the signal downfield to higher ppm values. In practice, protons typically show signals in the range of 0 to 12 parts per million, while carbons appear within 0 to 220 parts per million. This wide range allows us to differentiate between various atomic environments effectively. Understanding the chemical shift is like having a map to the molecule, helping us pinpoint functional groups and deduce structural information. Multiplicity reveals how a nucleus is interacting with its neighbors. From singlets to doublets, triplets, and beyond, it's a symphony of spin-spin coupling. The coupling constant, or J, measures the interaction strength between nuclei. It's expressed in hertz, and provides precise information about molecular connectivity. Lastly, line width. This tells us about the relaxation processes and can even hint at molecular motion or interactions. The image illustrates the chemical shift, delta, in NMR spectroscopy, showing the typical ranges for different proton environments. Carboxylic acids, 10 to 12 parts per million, highly de-shielded by electronegative oxygen and resonance. Aldehydes, 9 to 10 parts per million, de-shielded due to the carbonyl group. Aromatics, 6 to 8 parts per million, de-shielded by the ring current of the aromatic pi system. Amides, 5 to 8 parts per million, moderately de-shielded by the carbonyl group. Water, approximately 4.5 parts per million, affected by hydrogen bonding. Alcohols, 3 to 5 parts per million, de-shielded by oxygen. Amines, 1 to 5 parts per million, slightly deshielded compared to alcohols. Alkanes, 0 to 2 parts per million, highly shielded, depending on substituents. Tetramethylsilane, 0 parts per million, used as the reference peak. Chemical shifts depend on electronegativity, hybridization, hydrogen bonding, and resonance effects. Multiplicity reveals how a nucleus is interacting with its neighbors. From singlets to doublets, triplets, and beyond, it's a symphony of spin-spin coupling. The coupling constant, or J, measures the interaction strength between nuclei. It's expressed in Hertz, and provides precise information about molecular connectivity. Lastly, line width. This tells us about the relaxation processes and can even hint at molecular motion or interactions. Now, let's dive deeper into ppm, or parts per million, the unit used to measure chemical shifts in NMR spectroscopy. ppm is essential because it standardizes chemical shift values across spectrometers of varying magnetic field strengths, ensuring consistency in data interpretation. In NMR, the resonance frequency of a nucleus depends on the strength of the applied magnetic field, which varies between spectrometers. For example, a 400 megahertz spectrometer generates a different absolute frequency for the same nucleus compared to a 600 megahertz spectrometer. Without a standardized unit, comparing chemical shifts across instruments would be challenging. ppm resolves this issue by normalizing chemical shifts. It is calculated as the resonance frequency shift, in hertz, divided by the spectrometer's operating frequency, in megahertz, multiplied by 1 million. For instance, a 400 Hz shift observed on a 400 MHz spectrometer corresponds to 1 part per million. If measured on a 600 MHz spectrometer, the same chemical shift would still equal 1 part per million, even though the frequency in Hertz would differ. This normalization allows scientists to compare and share results seamlessly, making ppm a universal language in NMR spectroscopy. Integration in NMR spectroscopy focuses on the area under each signal peak, which directly corresponds to the number of nuclei contributing to that signal. It allows us to determine the relative quantities of different types of protons or nuclei within a molecule. Here's how it works. The area of an NMR signal is proportional to the number of equivalent nuclei responsible for that resonance. By analyzing these areas, we can derive the relative ratios of various groups within a molecule. For example, in a compound containing a methyl group and a methylene group, the integration values for their respective signals would show a 3:2 ratio. This reflects the 3 protons in the methyl group compared to the 2 protons in the methylene group. In summary, integration is a fundamental tool for quantitative analysis in NMR, providing essential information about molecular composition and structure. Let's analyze the integration in the provided NMR spectrum to understand how it relates to the structure of this molecule. The first peak we see at around 1.0 parts per million corresponds to the CH3 group, or the methyl group, in the molecule. The integration value tells us there are 3 protons contributing to this signal, which makes sense as the CH3 group contains 3 equivalent hydrogens. The peak is likely a doublet, indicating coupling with a single proton from a neighboring group. Next, at around 3.5 parts per million, we have a signal from the CH2 group located next to the oxygen atom in the structure. Here, the integration value indicates 2 protons, corresponding to the hydrogens in this CH2 group. The splitting pattern is likely a triplet, suggesting coupling with an adjacent CH3 group. The single peak in the range of 2.0 to 2.5 parts per million is attributed to the hydroxyl group, or OH. The integration value here shows 1 proton, which matches the single hydrogen in the hydroxyl group. This peak is often a broad singlet due to rapid exchange of hydroxyl protons, meaning it doesn't strongly couple with other protons in the molecule. Finally, the peak around 4.0 parts per million corresponds to the other CH2 group in the molecule. The integration value again indicates 2 protons. The splitting pattern here is a quartet, which occurs due to coupling with the 3 equivalent protons from the adjacent CH3 group. In summary, the integration values 1 to 2 to 2 to 3 correspond perfectly to the protons in the CH3, CH2, and OH groups in the molecule. Integration helps us quantify the number of hydrogens in each environment, and when combined with chemical shifts and splitting patterns, it provides a complete picture of the molecular structure. Multiplicity or signal splitting in NMR spectroscopy occurs due to spin-spin coupling between neighboring nuclei. This interaction causes the signal of a particular nucleus to split into multiple peaks, providing insight into the number of adjacent, non-equivalent nuclei. The pattern of splitting reveals the number of interacting neighbors. For example, a proton with one neighboring proton will produce a doublet, while a proton with two neighboring protons might produce a triplet, and so on. The resulting multiplicity, whether it's a doublet, triplet, quartet, etc., helps identify the molecule's structure and connectivity by revealing how atoms are connected to each other. In NMR spectroscopy, the splitting of peaks, known as multiplicity, arises from spin-spin coupling between non-equivalent neighboring protons. This splitting provides valuable connectivity information in a molecule. Let's break down the common splitting patterns you see here. The first peak is a singlet, which appears as a single sharp peak with no splitting. This indicates that the nucleus is not coupled to any neighboring protons, such as a hydrogen atom in an isolated group or in a symmetric environment. Next, we have the doublet, which appears as two peaks of equal intensity. This splitting occurs when the observed nucleus is coupled to one neighboring proton. For example, a CH group adjacent to a single CH3 group would produce a doublet. Following that is the triplet, a three-peak pattern with a 1 to 2 to 1 intensity ratio. This happens when the observed nucleus is coupled to two equivalent protons, like the hydrogens in a CH2 group adjacent to another group. The quartet consists of 4 peaks with an intensity ratio of 1 to 3 to 3 to 1. It results from coupling with 3 equivalent protons, such as a CH group next to a CH3 group. The coupling constant, denoted as J, is a key parameter in NMR spectroscopy that measures the separation between split peaks in Hertz. It reflects the strength of spin-spin interactions between coupled nuclei, providing valuable structural information. J values are influenced by the bond distance and bond angles between nuclei, making them a direct indicator of molecular geometry. For example, in alkenes, the coupling constants of cis and trans protons are distinct and help differentiate their configurations. Cis protons, which are located on the same side of the double bond, typically exhibit smaller coupling constants, ranging from 6 to 12 Hertz. This is due to the closer proximity and reduced torsional interaction. Conversely, trans protons, positioned on opposite sides of the double bond, display larger coupling constants, often ranging between 12 to 18 Hertz, as their spatial arrangement favors stronger spin-spin interactions. Coupling constants are not only limited to alkenes, but also provide insights into complex molecular systems. They help identify relationships between nuclei and reveal finer details about bond connectivity and orientation. In summary, the coupling constant J is an indispensable tool in NMR spectroscopy, offering precise insights into molecular structure and the spatial arrangement of atoms. The spectrum shows coupling between HA and HB, with the splitting patterns reflecting their interaction. Peak of HBE appears as a triplet, indicating coupling with two equivalent H protons. The separation between peaks in the triplet gives the coupling constant, a BJ-AB peak of HA. Appears as a doublet, showing coupling with a single HB proton. The spacing between peaks in the doublet also corresponds to JAB. The consistent coupling constant JAB, measured in Hertz, confirms the mutual coupling between Ha and HB. This value provides insights into bond distance and geometry, typically in the range of 6 to 12 Hz for adjacent protons. Line width is the width of an NMR peak at half its height and provides insights into molecular motion, relaxation, and interactions. Broad peaks often indicate dynamic processes like rapid tumbling or unresolved coupling, common in larger molecules or viscous samples. In contrast, sharp peaks suggest well-resolved interactions in smaller, stable molecules. Line width is particularly useful in studying biomolecules and dynamic systems, offering valuable information about their structure and behavior. The diagram shows the Lorentzian line shape, which describes the typical NMR peak. Amplitude, the height of the peak. Half-line width, the width of the peak at half its height, also called line width. The line width gives information about molecular motion and interactions. Narrow peaks indicate well-resolved systems, while broad peaks suggest dynamic processes or interactions. Key NMR measurements: chemical shift, integration, multiplicity, coupling constant, and line width provide essential insights into a molecule's atomic structure, dynamics, and surrounding chemical environment. These parameters are crucial for precise compound analysis, enabling the identification of functional groups, molecular interactions, and connectivity. By combining these measurements, NMR spectroscopy plays a vital role in advancing research, drug development, and industrial applications, offering unmatched capabilities in understanding molecular structures and properties. Thank you for your attention. I hope this overview has been helpful in highlighting the importance of NMR measurements. Feel free to share your questions or thoughts.